In this screencast, I'm going to give you an overview of the operation of the VGA timing controller and discuss what you need to do to complete this VGA timing lab. I'll assume that you've started to read the Nexus 2 manual on the VGA, so you have an idea of what's going on. The manual doesn't have all the details necessary to complete the lab, but should give you a good idea and will help as we discuss this lab in this screencast. You're going to create a controller for a cathode ray tube or a CRT. Even though we don't use CRTs anymore, the timing and control signals of the VGA cables use the same protocol for a CRT as they do for the LCD, for backward compatibility. It's helpful to understand how a CRT works in order for you to understand the timing signals and the video signals you need to create. You'll be creating logic to drive the RGB signals, those are the three color signals, and the timing signals, the horizontal and vertical sync. The CRT contains electronics here to steer the cathode ray. These signals steer a ray that draws a signal on the screen. The cathode ray then draws a color on the screen based on the values of the red, blue, and green. And so at any given moment of time, the cathode ray is pointing to a single location on the screen, and the color at that location of the screen is determined by the analog value of the red, green, and blue signals. Now the CRT does not randomly draw on the screen. It follows a very careful pattern by starting at the top of the screen, drawing a single line from the top left to the top right, and then moving back down to the next line. This is called the raster order. The raster order is shown in this figure. As the cathode moves from left to right, the red, blue, and green electron guns display a color at each location based on the values of the red, green, and blue analog signals on the VGA cable. When a single line has completed, the cathode ray must retrace by stopping its movement to the right and turning left and moving down slightly, as shown here. This movement of the beam from right to left is called a retrace, and no color is displayed on the screen. If a color was displayed on a screen during this retrace period, it would mix with the desired colors and mess up the image. In the figure shown here, the red line indicates that the actual colors are being displayed, while the black line indicates that no color is being displayed during this retrace period. The horizontal position of the cathode ray is controlled by an internal circuit that generates the current for the horizontal deflection coil. Notice this current is shown in this graph here. Notice that on the left the current goes up, indicating that the horizontal position of the cathode ray is moving. As soon as it gets to the end and during the retrace period, the current drops down, moving the horizontal cathode ray position back to the left of the screen. And this is a very periodic signal. It happens for every line. A retrace, display, and then a retrace. Fortunately, you do not need to create the circuit that generates this current. Instead, you need to generate horizontal timing circuits for the monitor. The CRT will use your timing circuit to create the proper horizontal deflection. As seen below, you need to create a horizontal sync signal to provide this timing. There are several components of this horizontal sync, such as the display period, the front porch, and the back porch, and we'll discuss these a little bit later in the screencast. After performing this display and retrace for 640 lines, so notice there's 640 pixels here, we do it again for 480 lines. So this retrace occurs for 480 times. And then the vertical trace we must actually bring to the top as well. So similar vertical sync signal is also provided to signal and the vertical retrace period. Like the horizontal sync, this signal has a display period, front porch, and back porch. Now you may be asking yourself, why do I need to understand how the CRT works? We're using a flat panel LCD in the class. You're right, we are not using a CRT, but as said earlier, the timing signals used on a modern LCD follow the same signaling requirements of the old CRTs for backward compatibility. The LCD contains a digital circuit that will interpret your VGA signals and recreate your display based on your signal timing. For you to create such an image on the screen, you must create the horizontal sync and vertical sync timing signals, as well as the color signal. The VGA connector uses a DB15 connector as shown in this slide, and there are 10 digital signals from the FPGA that are used to create the VGA signals. There are 8 digital signals for color to create the 3 different colors, analog signals, and 2 different signals, digital signals, that will create the timing signals. We'll begin by discussing the color signals and then describe the timing signals. The VGA cable has 3 analog signals for color, 1 for red, 1 for green, and 1 for blue. These are analog signals. These 3 analog signals then are mixed to create a custom hue. All colors that are visible to the human eye can be created by properly mixing these 3 primary colors. Your FPGA circuit does not have the ability to generate an analog signal. The outputs of the FPGA are either a 1 or a 0. However, circuitry outside the FPGA has been added to allow you to generate these analog signals from a set of digital signals here. These are shown by the resistor network. This carefully designed resistor network has been created that allows you to create a limited set of analog signals by driving the color signals with 1s and 0s. 3 digital signals are provided for red, allowing you to create 8 different voltage levels for the red. 3 different digital signals are provided for green, allowing 8 voltage signals for green. And 2 signals are provided for blue, allowing for 4 voltage levels for blue. With 8 digital signals for color, you can create 256 custom colors by mixing the red, green, and blue. To understand how an analog signal is created, consider the red signal. Assuming that the load of these analog signal has high impedance, the load here is high impedance. If the output voltage of a 1 on the FPGA is a 3.3 volts, and all 3 red signals are a 1, then the red analog signal will be a 3.3 volts, and the maximum red analog signal will be shown. If all 3 red signals are a 0, the I/O voltages on the red will be a 0, and the analog voltage for red will be a 0. And there will be no red component in the color that is displayed on the screen. If some of the red signals are high and low, the actual red voltage is determined by a voltage divider created by this resistor network. This example demonstrates the analog voltage created by the value 1, 0, 1. Red 2 is a 1, red 1 is a 0, and red 0 is a 1. The 3 digital signals create this voltage signal here. We have the red out with 2 resistors going high, 1 from red 2 and 1 from red 0, and another resistor pulling low for red 1. This circuit here is a simple resistor network, and using standard circuit techniques can be drawn this way. These 2 resistors are in parallel, resulting in a 406 ohm resistor and a 1 kilo ohm resistor. Using standard voltage divider techniques, we know that the output voltage of the red is 2.3. All other voltages can be determined using a similar technique. As it said earlier, 8 different voltages can be created with the 8 different values for red, green. The same thing applies for green, and then 4 different values can be applied for blue. The next important concept to understand is the timing signals. You'll need to create a horizontal sync signal, HS, and a vertical sync signal, VS. While the timing of each signal is different, they have a similar structure, and we'll describe the structure of the HS signal first. The horizontal sync signal is a periodic signal that has 4 components. It doesn't really matter which of these 4 different components or phases is first, since it's repeating. For the purpose of this discussion, the first phase we'll discuss is called the display phase. And this is the largest amount of time within the period. During the display phase, we have values being displayed on the screen in raster order from left to right. The color values on the 3 analog signals will be drawn in time during this display period. For this particular resolution that we're going to use in this lab, 640 by 480, there will be 640 pixels worth of time that are displayed in this display region. After the display region comes the front porch. This is part of the retrace in which no color is being displayed on the CRT. After the front porch comes the sync phase. During this phase, the HS signal is driven low. Like the front porch phase, no color is being displayed as we are blanking. The fourth and final phase is the back porch, and it is also blanking. Once the back porch is over, the display phase begins again, but provides the display at the next line lower in the image. In order to properly display an image, the timing of these phases must be exact. The timing of these signals is based on the time of a pixel clock. For the 640 by 480 VGA display resolution, a single pixel takes 40 nanoseconds and requires a 25 megahertz pixel clock. With 640 pixels in the display region, the total time for the display region is 640 times 20 nanoseconds, or 25.6 microseconds. The Nexus reference manual contains a table that provides the timing of each of these phases. The total time for a sync period, for horizontal sync period, is 800 pixel clocks, or 32 microseconds. As stated earlier, the display phase is 64 clocks, or 25.6 microseconds. The phases of other three regions is shown in this table: 16 clocks for the front porch, 96 clocks for the sync, and 48 clocks for the back porch. You will need to create a counter that counts from 0 to 799 to create this periodic signal. Now, it's important to remember that when we're talking about clocks here, we're talking about pixel clocks, which is the 40 nanosecond pixel clock, and not necessarily the 20 nanosecond clock that we're using on our FPGA board. What you'll need to do for this lab is to create a counter that counts from 0 to 799 and indicates the phase, each of the four phases of the horizontal sync. When the counter is a 0, you're in the display region. From 0 to 639, you're in the display region. Between 640 and some value that I'm not going to tell you now, something you'll need to compute on your own, is the front porch. The next phase is going to be the sync, and then finally the back porch. And so you'll create a counter that counts from 0 to 799, and then decoders that are used to decode when you're displaying and when you're applying the sync signal. Once you've created this counter that counts from 0 to 799, the first thing you'll want to do is to create a decoding logic that determines the value of sync, determines what values of the counter the sync should be low. After creating the horizontal sync and the decoding logic for this, the counter and the sync decoding logic, you'll also need to do the same thing for the vertical sync. The vertical counter is similar to the horizontal counter in that it has a display region, a front porch, a sync, and a back port region. The primary difference between the vertical counter and the horizontal counter is that the vertical counter should only be incremented at the end of each line rather than at the end of each pixel clock. And the amount of time in each region is different. In this figure, the amount of time for each region of the vertical sync is displayed in terms of lines rather than clocks. Each line consumes 32 microseconds, and the display time is 480 lines, or 480 times 32 microseconds. The number of lines for each of the other phases is shown here in your table. There are a total of 521 lines used in this in order to complete a full image, including the lines reserved for retrace. And you'll need to create a counter that counts from 0 to 520 and decode this counter to generate your vertical pulse. As described earlier, the timing for the VGA is based on a pixel clock. The pixel clock is 25 megahertz, or 40 nanoseconds. This is twice the period of our board clock, which is 20 nanoseconds using a 50 megahertz clock. One of the things that you'll need to do for this lab is to create an enable signal that prevents your counters from incrementing every clock cycle. Rather, your counters should be incremented every other clock cycle. So the circuit you're going to create will look something like this. You'll have a 50 megahertz clock coming from the board and an inverter that generates the pixel unenable. This will toggle every other clock cycle. Now this signal does not go into the clock of your counters because for reasons we'll discuss later, this will cause timing problems. Instead, we are going to use the same 50 megahertz clock on our counters, the horizontal and vertical sync counter, but we will only enable this counter from updating when its pixel enable signal is high. This is described in a little bit more detail in the textbook in the lab manual. So to summarize this screencast, you will need to create a horizontal timing, a horizontal counter that we'll call pixel X, and a horizontal sync signal. You'll also create a vertical counter, pixel Y, and decode that counter to generate the VGA sync signal. In addition, you're going to need to create a few timing signals. The first is a signal named blank, and this blank signal should be asserted whenever you're in the middle of a horizontal retrace or a vertical retrace. You'll also have a signal called last column that is asserted when you're in the last visible column, when your counter is a 639. And then finally, last pixel when you're in the last visible row. I hope this screencast has been helpful in understanding the information that's contained in the lab manual. At this point, you should be ready to start your lab and complete the timing. Remember that when you complete this lab, you will need a workstation that has a VGA display. These are towards the back of the room. You won't need it until you're passed off your test bench and ready to download it to the board.